Ladies and gentlemen, my name is Vaishnavi and I am from Infineon Technologies, Bangalore. And I hope you are doing well today and having a great time here. So today I will be presenting on a topic of virtualized ecosystem to envisage numerous application on an automotive microcontroller. So here, let us look at our today's agenda. It begins with an introduction on why are we trying to integrate virtualization technology into our automotive framework. And next will be a very brief introduction onto again virtualization technology for automotive domain, as it is already widely used in IT section. So I wanted to at least explain why virtualization, how virtualization is used in embedded domain. Then lastly, I'll be talking about our framework along with the advantages and future scopes that we will try to achieve in upcoming years. So first thing is, what does a future car needs? So today we can see how drastically our development of cars are, right? Digitalization, increase in automation, electrification, or even with the connectivities. So this is not just it. We can further see how it will like go on increasing the functionality of a car. There might be something else that can be added. So first thing would be a headroom to grow. Here, with the increasing speed of innovation, especially in the software-based systems, we will see how common it will become, how common it will be, uh, that there will be a demand for the upgradability of the functions in the car. High performance with the AI, more performance needed for the mobility and autonomous driving. Here, many operations that are being performed in car will require collecting data from the sensors. And currently, I think AI technology is mostly widely used here to provide the driver a safer, comfortable experience of driving. Next will be a new E2E architecture where I have seen, like I've noticed that E2E architecture will be taking over. Like it is now used a lot, and this will reduce the complexity of the device car. And looking at the trend now, we can tell that the E2E architecture will have to accommodate many advances in the automotive driving, expanded infotainment, or even with the 5G connectivity and so on. Like there will be multiple uh, zone-based architectures that might get just added in these upcoming modern cars. Fully connected, as the name says, a fully connected car would rely on the heads-up displays, audios, in-car entertainment, connecting the car to a cloud, or even with the, getting access to internet. Fast time to market, the technology is fast changing, like technology is changing very fast. And as the technology changes, we know that as a consumer we try to like we have our own demands. It will be raising, the demands will be raising, that will make automakers to respond to the market even faster than before. So here we can see that modern system contains a very large number of ECUs, and each containing a specific system to a specific criticality level, such as we can say that we have a brake system that is a very critical level, and even for a non-critical system such as entertainment system, or even with the interior lighting, that is not a critical system. So even for that, we need a lot of ECUs. This brings us to today's topic, that we have to take a note on how to how to take a new approach on integrating all these application software into a single hardware platform. So this is the main topic which we are actually trying to understand. But however, this might lead into increase in the system complexity, hindering the critical aspects and efficiency of the automobile. Now, protecting the integrity of the component from the faults of another is very essential. Like it's required in all the system. that is hosting multiple applications. So here the entire system could be compromised if one of the IPs or one of the system subsystem is not in a proper isolation. So again, for solution, as a solution, we are trying to adopt some new architectures or new technologies into already based our automotive architecture. And since and here I think we are trying to integrate virtualization as it's most promising among all the others which have uh, like which we have seen. And because it also has an advantages of providing software support for the partitioning and running multiple OS on a multiple heterogeneous OS and running tasks on these. Now, what is virtualization? So hardware virtualization refers to creation of virtual machine that acts like a real computer. So it's technically a virtual machine will be a virtual machine virtualization will be having a software layer, abstract layer, that will be called as hypervisor, and this will be sitting on the hardware, as you can see in the figure on the right side. So we have this hardware and we have a hypervisor, that is a software abstract layer, which will create virtual machines. And here virtual machines is just an execution environment typically that contains operating systems and software applications. Now here OS can be either fully fledged general purpose operating system or even the real time operating system. As we are in automotive domain, we need to have an RTOS. So this can be either of those. Now this opens up to the different combinations depending on the application requirement. Now, if you want multiple virtual machines to be sitting on a hypervisor, we can add up to that. But note that you have to limit usage of virtual machines just to tell that. Now here in Infineon Technologies, we have integrated this virtualization into our latest TC4xx, and which provides a customer up to 7 virtual machines. Here it is given in the pointer, that is freedom of interference. So hypervisor will provide us separation and isolation, and we have up to 7 virtual machines per core. And the hypervisor which we are using is a type 1 hypervisor that will provide us real-time embedded application. Now comes the question, where is virtualization suitable approach when we are trying to meet the requirements of safety assurance and sharing of hardware resources when implementing safety critical control system? Now to answer this question, it depends on the factors such as selection of your hypervisor and protection mechanism. Now hypervisor is a, as I showed in the figure before, in the slide before, we have seen that it's a most critical thing that creates our virtual machine. So here we have to we have some standards that a hypervisor needs to incorporate. First one would be real-time performance. Because we are in again automotive domain, real-time is a must. And secure encapsulation from the secure encapsulation, we need uh, like subsystems, because we have multiple subsystems in VM. It can enforce like communication, we have we should be able to encapsulate subsystems in a VM. And these VMs can these encapsulated VMs can provide us security policies for communication to and fro from one subsystem to another. Isolation between VMs related to the security, it is related to the security. So now if one virtual machine is doing its task, and it should not bother the other virtual machine which is performing its own task. So this is what we want to do. We do not want any interference between these two virtual machines. Next one will be scheduling policy. So scheduling policy is depending on a hypervisor. So here hypervisor will be the one which schedules virtual machines according to its resource partitions or policy priorities. This is again overview of hypervisor that our TC4xx has. We have new execution mode, VM execution isolation, resource isolation. So to add up with the point of resource isolation for VMs, we have this protection mechanism that I'll be talking in a future slide. We have this fine grained protection and allocation of resources to a particular virtual machine. Interrupt isolation to VMs. Here again, we have a routed interrupts for a specific virtual machines. Use like if one VM1 is receiving a interrupt, it is directly routed to that said VM. And if you notice the figure in the right side, we this is what we are trying to achieve in our achieve. So in virtual machine, you can see there are four IP, IPO, IPJ, IPR, and IPD. So these are different IPs that we are trying to incorporate in one virtual machines, and same IPs can be used in different, but we just want to see if there is any issue with the virtual machines that are having same IPs. Next one would be execution view. Here we have these core context registers that are triplicated to create an independent hardware resource set. So multiple resident, we have VM, we have here HR0. HR0 is where hypervisor will reside. So it is just for hypervisor, and none other virtual machine can use it. HR1 is for a privileged virtual machine that resides in HR1. So here privileged virtual machine is also, I can say that it is for real-time operating system. This can also provide our real-time execution. This is why we want it to be in HR1, so it can be easily like context. We can easily context switch between HR0 to HR1 with very low overhead. HR2 here is shared among the VM2, VM2, VM3, and till VM7. So these are shared. And if we want to use VM3, then VM3 when VM2 was running before. If VM2 was running before and we want to use VM3, we just have to have a context swap between the hardware resources. Still, the hardware resource will be HR2. In the note below, we have given the possible HRX transitions. So HR0 to HR1, HR0 to HR2. Access protection. As I told you before, there is a special protection mechanism that we are using in our TC4xx, and that is a PROT and APU mechanism. These access protection mechanisms can be used to assign on-chip resources like system function, CPU, so for this like system function, CPUs, memories, and communication functions. Now with the PROT mechanism, I can say that PROT mechanism is an ability where we can assign a master to the like we can give the ownership to a single master agents. Like we have multiple masters such as CPU, DMAs, PPUs. So we can just pick one of it, and that will be a master. And this is mentioned in a set of register that is a it is mentioned in a prot register. We have a special location which we can mention, like who would be the master for the prot. Uh, APU APU is again a protection mechanism that is like doubling the protection. First, already we have protection. We get the protection from hypervisor, okay, but still we are updating and upgrading our protection using prot. Now again, prot and APU can provide us extra step for protection of memories. Now here with APU, we have access protections that will provide us fine-grained control of the protection system of a group of registers. So it will be like APU will be able to configure the region of a memory. Like if we want to use a memory region, we can use APUs. And this also provides us no access, read only access, write only access, or even both read and write access. That that I'll be mentioning in the next slide, why we need APU. So here, this is the application framework for our project. So here we develop the test case using the embedded C, and we have the libraries that supports these test cases. We run it on a simulation platform prior to trying or integrating all this virtualization framework. And this is tested on EDA tools from Synopsys or Cadence, taking note that there is no error prior to adding all this virtualization. Once we are sure that there is no error in the test cases, we are integrating these test cases into our framework integration. And here, note that before in the previous slides, I told that Infineon can provide up to 7 virtual machines, but for our convenience, we are just using 4. So don't be confused with why we just have 4. That is just for our convenience. And here the strategy was to place the specific codes or specific test cases into multiple virtual machines, uh, and to ensure that the majority of virtual machines are enabled. And with the test cases, we are also trying to see how our microcontroller is tested. Uh, Hereafter, integrating test cases in virtual machine, we can run. We have the output file, so that we are running it in emulator. And because we already know the results from the simulation, we're just checking if there is any error or if there is any problem while we are integrating that into virtual machine virtualizations. And if there is, we are trying to just try to balance it out. And this whole framework, we have created this even prior to the arrival of our silicon. So again, this is just a zoomed in block diagram of how our application software looks in that virtualized framework. Note that like here we have a DMA0, DMA1, and PPUC. Uh, and for DMA0, if you see that we have 4 blocks in each virtual machine. Now for TC4xx, we have DMA with the 128 channels, and we are segregating these channels into 32 channels per virtual machine. Similar to the DMA0, we have DMA1 with the 64 channels, 16 channels per virtual machines. And also note that for DMA, we have this hardware resource partitioning that will isolate the DMA channels from each other. So again, we have extra protection such that none of the channels will be interfering with other channels. Here we are just and PPUC here, it will just perform our normal Fourier transform, and DMA0 and DMA1 is just sending data from source to destination that is mentioned in LMU regions. Here we are just expecting the data transfer from DMA without any data corruption. So if there is any data corruption, we have to check why it is so, because we already know that that was not the case before. Receiving the LRAMs if there is any trap generated for accessing the unauthorized LMU regions. So this unauthorized LMU regions is explained in this whole table. So we have channel number 0 to 15 in virtual machine 1 with the hardware resource partitioning of RP0, and APU master would be DMA0. Its source address will be located in LMU0. It has a write access. It does not have any write access, and but we can read from the LMU0. Destination address for this DMA will be in LMU2 with the write access but not read access. And this read and write access will be provided by APU. That is what I was telling in the previous slide. We can use APUs to give the read and write accesses to the set of registers. So here our APU is used in the memory region. Similarly, for 16 to 31, we are using virtual machine number 2 with the HRP as RP1. APU master would be DMA0. Source location is in LMU1 without write access, but with read access. Destination would be in LMU3 with write access and without read access, and so on. It will continue up until 127 channels. That is all together 128. So 12 to 127 channel with the virtual machine 7, RP7. APU master would be in DMA0. Source will be in LMU5. The destination would be in LMU7 with the respective access protections. Similarly, for DMA0, we have DMA1 also, because this is again with 64 channels, and it is segregated as shown in the table. The function here of APU in DMA is just to like if there is any attempt to access the unauthorized channels, if unauthorized channels, or even with the LMU regions, if DMA, for example, if DMA1 is trying to access LMU3, then it must lead us a trap. So that is one thing. Next will be allowing the transfer operations which obey the access policies. Third one is DMA channels under HRP is configured by the protection mechanism that can request DMA services. This is like total block diagram of how we will figure like we are trying to explain our framework. So we have hypervisor, we have 4 virtual machines in it. We have DMA IP, we have PPU IP, we have interrupt router, so on. Now, advantages of virtualization. Here, first of all, we can say that it reduces the cost of system design. The ability to run the concurrent operating system on a single processor core can reduce the bill and bill of the materials, especially for the low end devices. So here we can see that instead of using multiple hardware resources, we are just trying to integrate it into a single hardware. So that is why we can see like reduction in cost. Improved reliability and robustness by reducing the effect of failure in single virtual machine. Now here, because virtual machine are encapsulated as a subsystem, so it's failure. So if there is a failure in one virtual machine, it will not create any effect into the other because of the isolation that that a hypervisor provides. Reduce the effort and timing required to revalidate of systems after making changes. Next, protection access mechanisms offer secure encapsulation. We have seen that at least we can get up to 3 protection mechanisms. Like we have a good packed up protection mechanisms in this virtualization. Merging multiple ECs will again reduce the hardware required. So future scope here would be our learning that can be implemented on non-safety critical applications. So here now we are using critical applications, like we can use non-safety critical applications. Planned hardware feature extensions are aligned with the major hypervisor vendors active in real-time embedded systems. And these are the 3 which we are planning on to. So hypervisor vendors, one is Cisco, Electrobit or Open Synergy. Launching different operating system of virtual machines. So this is the most important thing. We are trying to add multiple OSs because we know we can run multiple OS in virtual machines. We have such like exposure. We can use RTOS in VM1, GPOS Linux in VM2. We can run Windows in VM3, such that we want to try to explore how different operating systems can be run on our virtualization framework. That's it. Any questions?